So we're told the ball falls vertically, strikes a smooth fixed plane. Plane is inclined at an angle of beta. I've actually called it theta here by accident, so I'll be working with theta. And we're only doing part 1, so prove that tan theta is equal to the square root of E. So particle falls down, rebounds out horizontally. If that's theta, that has to be theta as well because they're alternate. There's 90 degrees here because of vertical and the horizontal lines. Then 180 in the total angle. So that works out as 90 minus theta there. All right. If that's 90 minus theta there, we'll use that in a moment. But in this case, look, you can see that that angle and that angle are opposite angles. So they have to be equal. And then there's an angle between that and that, which is 90 degrees. So that's 90 minus theta. So I've done it 2 ways, right? Now what we need to do is rotate the plane through an angle theta clockwise so that the plane becomes horizontal. And that's what I do here. So I have the speed going into the collision, which I call u in a moment. I have the angle, 90 minus theta. If that's a right angle, that works out as theta. So what we get then is, to get this thing, that's the opposite there. It's the opposite of the angle theta, and that's the adjacent. So to get the opposite, we need to use the sine. So sine of theta is equal to the opposite over the hypotenuse, which is u. So the opposite works out as u sine theta. And then the adjacent will work out as u cos theta. Different to what we've experienced previously, but then the angle is in a different place. So that's why the cos and the sine are swapped there. Now, the first thing you always want to do here with these is write the vectors in I and j form, which is why you got the sine and the cos, and that gives me that thing. So the initial velocity vector is in the negative I direction and the negative j direction, so u sine theta I minus u cos theta j. Remember that if the particle comes down and rebounds back, the impulse is experienced vertically, so the j component changes. So it's that one that changes. So put the j component, which is u cos theta, into E is equal to minus v over u. And I've just rearranged it to give me that. That's it subbed in. So that's the velocity in the j direction after the ball hits off the plane. So the velocity vector then, the i's have stayed the same, and the j1 has changed. So that's where that's coming from. Now, that's kind of your steps with all of them. You need an initial velocity vector. You ask yourself, what way does the impulse go? And then that component changes, and you get the final velocity vector. The last thing you need to do now is prove that tan theta is equal to the square root of E. So we already had theta here, which is the same as theta there when we rotate it. That's the velocity afterwards. It's the velocity vector afterwards. So let's get tan theta with that thing by putting the j's over the i's. So tan theta would be that divided by that. Again, just taking the positive values. So I get tan theta is equal to E u cos theta over u sine theta. When I rearrange that, I get E on its own is tan theta by sine theta over cos theta. And sine theta divided by cos theta is tan theta. That's in the log tables. So we have tan theta by tan theta, which is tan squared theta. Get the square root of both sides. Tan theta is equal to root E.